So in the next section, we will look at what is black body and how we can actually use the concept of black body and gray bodies to calculate the emissive power of that object. So when we talk about thermal radiations, for example, just like any other form of radiation, when an incident radiation fell on an object, it can have three outcomes. So either that incident radiation can reflect back to the surrounding where it came from, it can refract, or it can pass through the object, and the third thing is that it can get absorbed by the medium or by the object. Okay, so based on that, we can actually define three different behavior or three different classes of objects. We can have opaque object, transparent object, and semi-transparent object. So what are these? Let's have a look at in the next slide. So an opaque object is when, for example, so this is your object here, okay? And if some form of thermal radiation, incident radiation hits this object, so if the major part of this radiation get absorbed by the this object, it means that the energy stays inside the object. This kind of object, what we call opaque objects or opaque mediums, and because the energies get absorbed by the object, it is going to increase the internal energy of the molecules, and as such, it's going to cause an increase in temperature. Okay, so one example of that is wood, for example. So wood is an opaque object. Then we have second type, that is transparent medium or transparent object. So for example, if the incident light is hitting this medium, this object, but major part of that light just passed through the medium, then it means that we have an transparent object. It means that the light is not going to be absorbed, and as such, there will be a negligible change on the temperature of this object. And for example, we have air. That is one good example of transparent object, because when the sun heats, for example, the rays heats up the air, it does not change its temperature enormously, just a slight change in temperature. And finally, we have the semi-transparent object. So semi-transparent object is when the incident radiation hits this object, some part of it can be reflected back, some part of it can absorb, and some part of it can be transmitted. So it can have all three effects. And in that way, the radiation can slightly increase in temperature, but not as for the case of an opaque medium. Okay. So based on this, for example, classification of different materials, we can actually define our black body. So black body is an ideal body that the concept was developed just to generate a hypothetical model. So black bodies are just hypothetical models and provide us the ideal conditions. Okay. So according to that definition, a black body is an object that absorbs all the thermal radiation falling on it. Okay, so there is no transmission and no reflection. It means that everything that fell on this object is get absorbed. Okay, so that is one condition of being in a black body. And the second condition is, or second feature of this black body is that this black body can emit the maximum possible amount of thermal radiation. Or in other ways, you can say that whatever it absorbed can be emitted completely from this object. Okay. While in reality, we have, for example, we have the real bodies, and these real bodies are more common in nature. So a real body is a kind of a semi-transparent. Okay, so it reflects and transmits some of the incident radiation, and the other get absorbed. Okay, so it means that the absorption of the radiation is not 100%. At the same time, when this gray body or the real body emits the radiation, it is also less than the maximum possible radiation. For example, in the case of black body, 100% energy can be emitted, while for the case of gray body, maybe 80% of the energy can be emitted. It means that it is not a perfect emitter. Okay, so these are the real bodies. One example of a black body, or one object that can be considered as a black body, is sun. for example, because sun is emitting continuously the maximum amount of energy. And one example of gray body can be, for example, Earth or any object that is actually absorbing some of the energy but is not reflecting back 100%. Okay. So now, in order to calculate what is the maximum emissive power, or the total power that is emitted from a black object, we can use the Stephen-Boltzmann's law to calculate that emissive power. Okay, so Stephen-Boltzmann's law gives us the total emissive energy from a black body that is equal to sigma, that is Boltzmann constant, times the absolute temperature of the surface of that object, and raised to the power 4. Okay, and this EB is, as I said, is defined as the emissive power, so that is watt per meter square, so that is energy falling on an area that is a meter square, so that is the energy flux. Okay, and then we have sigma, that is a constant, and it is always with the same value of 5.67 10 to the power minus 8 watt per meter square per Kelvin raised to the power 4, and Ts, that is the absolute temperature of the object. So by using this equation, we can calculate what is the maximum amount of energy that can be emitted by a black body at a certain temperature of at an absolute temperature of surface, that is Ts here. While in reality, as I said, that we do not have black bodies, we have what we call real bodies. So for the case of real body, it does not emit the maximum amount of energy. Okay, so it means that we can only emit a proportion of energy of a black body. Okay, and to calculate that proportion, we use the term here that is called emissivity. So Eg, that is the energy emitted by a gray body, is equal to emissivity times Eb, that is the maximum possible energy from a black body, times the fraction of that the gray body is going to emit. Okay, and if you put the value of Eb from the previous equation, so energy emitted by a gray body is equal to epsilon times sigma times temperature raised to the power 4. Okay, so this epsilon is actually the emissivity of the surface. Okay, and in other way to explain is that it is the fraction of energy, the fraction of the energy of a black body that a gray body is going to emit. Okay, and because of that, it's a fraction, so the value of emissivity will be between 0 and 1. Okay, so always the value of epsilon between be 0 and 1 to give you the nature of the surface. If epsilon is 1, it means that you are very close to a black body behavior. If it is lower than 1, it means that you are far from black body behavior. Now, sometimes we need to know the amount of energy which is emitted by a black body per unit time, per unit surface area of a particular wavelength. Okay, so in the previous slide here, for example, when we are talking about this EB or EG, this is the energy emitted irrespective of the wavelength. Okay, so we are considering the whole range of wavelength of radiation that are coming out of the object. While sometimes we want to know what is the particular wavelength of the energy. Okay, so in that case, we want to know, for example, the energy coming out of the object at a particular wavelength. So then in that case, we use the Planck's law, and the Planck's law is given here. So EB, so here lambda represent that this energy is coming at a certain wavelength and a temperature, or from an object at a certain temperature, and this EB lambda is equal to this equation here. So C1 and C2 are the constant values, so it means that they don't change, so we can always use the same value of the constant here, while we have lambda, that is the wavelength range, or the wavelength of the light, and temperature, that is the absolute temperature of the object. Okay, so this EB is different from the EB from the, for example, from the Stephen-Boltzmann law, in the sense that this is based on a particular wavelength, while for the case of Stephen Boltzmann law, the EB, that is the emissive power, is irrespective of the wavelength. Okay, and this energy, if you look at it here, you can see that in terms of the unit, so you have watt per meter square, that is the energy flux times the micrometer, and this micrometer actually comes from the wavelength of the light. Okay, and now if we look at the variation of the for the case of black body, if we look at the variation of emissive power in terms of its wavelength and the function of temperature, so we have EB, that is the emissive power from a black body, and lambda is the wavelength of that energy, or that wave. So if we plot that as a function of temperature, so we get this kind of graph shapes. Okay, so each of these graph is at a certain temperature. So there are a few things to notice here. So one thing is that wavelength and this energy is actually a continuous function of wavelength. So you goes, for example, for this particular temperature of 100 Kelvin, the wavelength with the increase with the wavelength, for example, the energy first increases, reaches a peak, and then it decreases. So it's a continuous function. And if you change the temperature, the wavelength, or the peak of this wavelength curve, is actually shifting to the left. Okay. So for example, here for the case of 100 Kelvin, you have a value of, let's say, 0.5. Now for the case of 500 Kelvin, this peak actually moves to a value of, let's say, 100. So there is an increase in the peak value with increase in temperature. Okay, and that's what is explained here. So now this peak in temperature, we can actually calculate it by using Wien's law. So, for example, this left shift of the curve, we can, as I said, we can explain it with Wien's law, and Wien's law give us the lambda t, that is the maximum power, or the energy where the EB would be maximum, is equal to B over T. Okay, so B is a Wien's constant, so it means that the value of B will not change. So the only thing that is controlling the maximum wavelength, or the wavelength at which the energy will be maximum, is the temperature of the surface. Okay, so if you remember in the previous slide, I said that the amount of energy that is emitted by a black body or by any body depends on two things. One is the nature of the surface, that it is a black body or a gray body, and the second thing is the temperature. So by changing this temperature, we can calculate what is the wavelength at which the energy will be maximum. Okay, so that is all for this part, and in the next part we will look at the heat radiation absorption for an enclosed system, and then we will talk about absorptivity, that is another important property of the material. Okay, thank you for your time.